time harmonic voltage. Instantaneous phase phi t here is omega t. So what we observe is that the instantaneous phase of this time harmonic voltage is totally dependent on time and on angular frequency omega. So now if I want to find the time period for change, so as you know that it's a sinusoidal, we have a sinusoidal voltage here. So whenever we have a phase change of 2 pi, we'll have a change, a time period we can calculate from that. So we equate omega capital T, T is the time period equal to 2 pi. So I can find out capital T as 2 pi by omega, and you know that omega is 2 pi f, so the time period for change will be 1 by f. We can find the time period for change for this time harmonic voltage from the frequency as 1 by f. So this means after each time period t, this waveform is going to repeat itself. This waveform is not going to change. After every time period of capital T, this time harmonic voltage is going to repeat itself. So let us look at this kind of time harmonic voltage pictorially, so it will be better to understand using a picture. So let's say this is the y-axis. Y-axis signifies the voltage Bt is equal to B0 sine omega t, and this is the x-axis is actually time here t. So the variation of this Bt of time harmonic voltage with respect to time can be represented by this waveform. It's a sinusoidal wave. So now B0 is the peak amplitude of this time harmonic voltage, and the time period of change is capital T. So this is a time harmonic voltage. Now next question is, I want to get a wave from this. I want to have a time harmonic voltage wave. I just don't want time harmonic voltage, but I want to have a time harmonic voltage wave. That can be illustrated from the next diagram we'll consider. So let's say at time t is equal to 0, at a distance z is equal to 0, that is at the origin, there is a time harmonic voltage Bt is equal to B0 sine omega t. So what does it look like? It looks like this sinusoidal wave here. So now we'll make some addition here. So basically what we'll assume is that this time harmonic voltage will start moving along the z-axis with a phase velocity of Bp. Bp is the phase velocity of this time harmonic wave. So after some time we'll have this wave along the z-axis like this. So now we want to consider any arbitrary point along the z-axis, let's say point B, and so let's say the distance of this point B from the origin point A is z. So how much time it takes for the wave to reach this point B? Since we know the velocity was B phase, Bp, distance is z, I can find time as z divided by the B phase. So distance divided by the speed will give me the time. So time it takes for the wave to reach from the origin to the point B will be z divided by B phase. From there, once I know the time, I can find the phase change. So let us do that in the next slide. So this is basically a time harmonic voltage wave. Now I want to find equation for this time harmonic voltage wave. So we are considering any arbitrary distance z at point B from the origin, and we want to find the phase difference of point A and B. So that phase difference we calculate as omega. Omega is the angular frequency into time it takes for the wave to reach the point B from point A. So distance is z, so phase velocity B phase, so time it takes for the wave to reach point B should be z by B phase. So now we also know that omega by B phase is basically your phase constant beta. So I can represent this expression of the phase delay as simply beta z. So now we can write the expression for time harmonic voltage wave at any arbitrary point B as B0 sine omega t minus phi phase difference between the point A and B. We have already calculated that, so let us substitute that. So the expression for time harmonic voltage wave can be expressed as b0 sine omega t minus beta z. So now what we can observe is that once I have time harmonic voltage wave, the phase here is omega t minus beta z. So this phase is dependent both on time and space. So omega t minus beta z. So we have a wave now. So now at the initial time t is equal to 0 at the origin, if the wave was having an initial phase of phi 0. So we have considered that wave was not having any kind of initial phase, but let's say we consider any wave which is having an initial phase of phi 0. In that case, I can generalize this expression for time harmonic voltage wave and write it as v0 sine omega t minus beta z plus phi 0. Phi 0 is the initial phase of the wave. So there is an interesting observation here we can make. Let's say the initial phase of the wave phi 0 was pi by 2. Then what happens to the expression for the wave? The expression for the wave will simply now become b0 sine omega t minus beta z plus pi by 2. Pi by 2 is the initial phase of the wave. So now sine of pi by 2 plus theta is simply cosine of theta. So you can express the wave equation as b0 cos omega t minus beta z. So this is the usual expression you have for the wave. So we'll have cosine of omega t minus beta z. So you can observe that phase is now both dependent on space and time. So this becomes a wave now. So now we can also represent, there is another very popular way of representing the wave, and it is in the form of exponential function. Some of the people write the wave in exponential function, but let's look at that expression. So let's say I actually have b0 exponential j omega t minus beta z. So this is a wave which is propagating along the positive z direction, and what I can do is I take the real part of it. See, basically you have Euler's function e to the power j theta is cos theta plus j sine theta. So here your exponential j omega t minus beta z can be expressed as cosine of omega t minus beta z plus j sine of omega t minus beta z. You take the real part of that, what do you get? You get the equation of the wave, b0 cosine omega t minus beta z. So this is another way of representing a wave. We usually represent wave which is propagating along the positive z axis as exponential j omega t minus beta z. So this is also an equivalent expression of the wave. So now we have the expression for the wave, and based on the expression for the wave, I can also find out different kind of waves. There are three common waves. One is called cylindrical wave, spherical wave, and plane waves. What are these different kind of waves? We will find answer in a very intuitive way. So later on we'll find it in a mathematical way. We'll directly use Maxwell equations and find wave equation and solve it and get the cylindrical, spherical, and plane waves. But now I want to introduce it in an intuitive way so that you understand the wave concepts more properly. So let us classify waves. How do I classify waves? For classification of waves, I have two parameters. One is the wavefront, another is the source of the wave. Different source of the wave will have different waves. And another thing is that looking at the wavefront of the wave, I can classify the waves. So waves can be basically classified into three: spherical, cylindrical, or plane, depending on the wavefront shapes. What is this wavefront shape? We'll discuss in detail, but let us define it. Wavefront is basically the surface of the wave of constant phase. So on this surface of the wave, the phase for the wave should be equal. So we'll see that using diagrams in the next slide. So basically on the surface of this wave, there is a constant phase. Phase is equal. And you will observe that this wave fronts actually your propagation wave vector is perpendicular to this wave front. So your wave vector, propagation of the wave vector will be always perpendicular to the wave front. These are the two observations you can make. First is that your surface of wave has a constant phase, then we call it wave front, and at the wave front the propagation vector will be perpendicular to the wave front. So now based on the different shapes of the wave front, we can have spherical wave, cylindrical wave, plane waves. We'll discuss in detail later on. And based on the source also, see, for different waves we will have different source. For example, if you want to have a spherical wave, you can have a point source. Usually we assume a point source with isotropic radiation in all directions, then we can actually produce spherical waves. Or let's say if we have a line source will give you some kind of cylindrical waves, line source. And if you have a 2D source, a planar source, then you can have plane waves. And another concept is that whenever you consider your source and observation are at infinite distance, most of the waves turns out to be plane waves. We'll discuss all of this in the next slide, in the following slides. First, let's consider what is a spherical wave. So we want to see what kind of wavefront and spherical wave produce, what kind of source this spherical wave will have. Just before that, let us try to refresh your fundamentals on the spherical coordinate system. So what is a spherical coordinate system? And as I know that all of you know what is rectangular coordinate system. Rectangular coordinate system will have x, y and z, and this is very simple for all the students. So let me define these variables we have for the spherical coordinate system. I think many of you may be knowing, but some of you may be confused. So let's see. Let's consider any arbitrary point in the xyz space, and position vector r is denoted like this. So distance of the point from the origin is called the position vector, and we usually denote it by r. And the angle this position vector r makes with the z-axis is called theta. And now you have to take a projection of this position vector r on the xy plane and find the angle it makes with the x-axis, we call it phi. So this is the variable r, theta and phi for the spherical coordinate system. So we'll be using it later on. So I want to define it properly. You know what are the variables for the spherical coordinate system? R, theta and phi, and they are shown in the figure. So now let us discuss about the spherical waves. What kind of source it will have, what kind of wavefront it will give. So let's consider a source, isotropic source, point source, and assume that this point source is radiating fields equally in all directions. So these are the EM waves. This point source is radiating equally in all directions. You consider a wavefront, a spherical wavefront. You consider a spherical wavefront, and it is at a distance r from the origin. So now along this spherical wavefront you find the distance. Distance will be always r. So now you know the speed of EM waves, it moves at the speed of light, and I want to find that see, basically I know the distance, I know the speed of light, I can find the time it takes for the wave to reach this spherical wavefront. So what you are observing is that distance is fixed, speed is fixed, so time it takes for the wave to reach this along this spherical wavefront will be equal. So if the time takes for the wave to reach on this spherical wavefront is equal, then phase will also be equal on this spherical wavefront. So we have a spherical wavefront here, all the phases are equal. So for such kind of source, point source will have a spherical wavefront. So spherical wavefront, we know that phase of wave on this surface is equal. So we have a spherical wavefront here, and look at the direction of the wave vector. Wave vector is radially outward, then it is always perpendicular to the spherical wavefront. So when we have a point source, isotropic source which radiates equally in all directions, will form spherical wavefronts. And we also know that the wave vector which is radially outward will be perpendicular to the spherical wavefront. So such kind of waves with the source, isotropic source, will give me spherical waves. So two things, one is spherical wavefront, another is the source. Source is a point source, then we'll have spherical waves. Let us discuss this spherical wave and find the equation of wave intuitively, not from the see, we'll find it intuitively, mathematical way. The most accurate way we'll discuss in the following class. So let's consider the spherical waves. And you see that the source for the spherical wave is a point source. It doesn't have any dimension. It's a zero dimension. Spherical waves is produced from point source with zero dimension. And what do we see? We see that spherical waves will be produced from the point source. Since the point source was radiating fields equally in all directions, the wavefront we are getting is a spherical wavefront. And if we are considering at a distance r from the origin where your point source is located, the area of this spherical wavefront will be simply 4 pi r square. And as the wave moves outward to a further and further distance, this area 4 pi r square will increase. R is increasing, then 4 pi r square area of this spherical wavefront will also keep on increasing. So now from the energy conservation principle, energy must be conserved, power must be conserved. So we need to have a proper Poynting vector. So Poynting vector, or let's say in a simpler term we call it power density. Power density, what should be the variation of power density so that power is constant? Since the area is 4 pi r squared, power density should be proportional to 1 by r squared so that power is constant. So let's see, if I want to find the power, I multiply the power density and the area. So area of the wavefront is 4 pi r squared, and if I assume that power density is 1 by r squared, in that case when I multiply this power density and the area, I am getting 4 pi, which is a constant and independent of r. So power must be constant for this wave, because we are assuming that this wave is propagating in a lossless media. So power should not change. There should be conservation of energy. And you will also know that the power density is directly proportional to amplitude square of the amplitude of the wave. So if power density is varying as 1 by r squared, then amplitude of the wave will be varying as 1 by r. So now we will have an idea to write a simple expression of spherical wave function. So spherical wave function would be of the form b0 by r. Amplitude will be dependent on 1 by r, and we'll have cosine of omega t minus beta r. So here we see that the phase is varying with respect to distance and the time. So we have a wave equation here, and even the amplitude should also vary as 1 by r. So this is the simple expression we can find from the intuition of a spherical wave. We'll mathematically find it out in the following classes. So that was about the spherical wave. We have another wave which is called cylindrical wave. So let us discuss that. In order to understand the cylindrical waves properly, you need to refresh your fundamentals on the cylindrical coordinate system. So everybody knows what is XYZ coordinate system, rectangular coordinate system. What is cylindrical coordinate system? So let's look at it. Let us consider a cylinder, and the radius of the cylinder is denoted by rho. So this is the first variable for the cylindrical coordinate system, radius of the cylinder. And this rho vector, let's say it makes an angle phi with the x-axis, and that angle phi is the next variable for the cylindrical coordinate system. We have one more variable which is the height of the cylinder, which is denoted by z. Rho, phi, z are the coordinate for variable for the cylindrical coordinate system. So we have discussed about the cylindrical coordinate system. Let's discuss about the cylindrical wave. What kind of source we should consider to have cylindrical waves, and what kind of wavefront it will produce. So let us see that in the next diagram. So for the cylindrical waves, as I have told you before, we should have a line currents. Let's assume a line current of this form like this. So now every current source here will be radiating fields in all directions like this. So now let's consider a cylinder at a distance rho from the cylindrical axis. So you consider a cylinder of radius rho. How do I draw it? This is a cylinder. This is a cylinder of radius rho, and let's say height is s. So now, looking at this cylindrical wavefront, let us look at the phase. Let us try to find the phase. So sources are in the axis of the cylinder. The distance of the cylinder from the axis of the cylinder is at rho. It is equal and it is rho. So on the cylindrical surface, distance is always rho, and you know that velocity of the phase velocity of the wave, let's say if we assume it's spherical EM waves, then it will move at the speed of light. Speed is fixed, distance is also fixed on this surface, so time it takes for the wave to reach this cylindrical surface will be same. So if time it takes for the waves to reach this cylindrical surface is same, then the phase will be equal on this cylindrical surface. So now we have a cylindrical wavefront. So the condition was phase should be equal on this surface of the wave. So for such kind of line current density, what we are observing is that if we consider a cylindrical surface, then the phase is equal, so we have a cylindrical wavefront. And let us also look at the other point. If the wave is vector is radial in direction, what we are observing is that wave vector is perpendicular to this surface, cylindrical surface. So what we are seeing is that when I have a line source, the wavefront it produces is a cylindrical wavefront and will have cylindrical waves. And in the next slide, let us try to find intuitively what should be the equation of such kind of cylindrical waves. So what did we observe? We observed that cylindrical waves are produced from 1D source, line source. 1D source, one-dimensional source, line source, and basically it produces a wavefront which is cylindrical in shape. And if you consider that wavefront is at a distance rho from the cylindrical axis, the area of the wavefront will be 2 pi rho h, and h is the height of the cylinder. So now this area is changing with rho. If we increase rho, the area is also increasing. So now, but from the conservation of energy, power must be constant, energy must be constant. So the variation of power density should be varying as 1 by rho. So if power density is varying as 1 by rho, when I multiply power density and power, I get the power. Power density and the area, I get the power. So power density is varying as 1 by rho, area is given as 2 pi rho h. When I multiply it, I get the power. Power is turning out to be 2 pi h, which is a constant independent of rho. So power must be conserved, power should be constant. If we assume the wave is propagating in the lossless medium, energy must be conserved, power must be conserved. So what we are observing is that in order to have that condition of conservation of energy, power density or Poynting vector should be vary as 1 by r, 1 by rho, and rho is the radius of the cylinder or cylindrical wavefront we are considering. So now, since you know that power density or Poynting vector is directly proportional to square of the amplitude of the wave, so the amplitude of the wave should be varying as 1 by square root of rho. So now then we can write the possible and simple expression of a cylindrical wave function. The amplitude should be varying as 1 by rho, so we should have b0 by square root of rho. So amplitude should be varying as 1 by square root of rho, and power density must be varying as 1 by rho. So the expression for a cylindrical wave function would be b0 by square root of rho cosine of omega t minus beta rho. So the phase now is dependent on time as well as the distance rho or the radius of the wavefront rho. So this is a simple and possible expression of a cylindrical wave function. So we have discussed about the spherical waves, what are the sources, what kind of wavefront it gives, what is the equation of the wave. We have also done the similar kind of analysis for the cylindrical wave. What is the source, what is the wavefront, and what is the equation. The last wave, which is the most common wave, is called plane waves. So we'll do similar kind of analysis for the plane waves in an intuitive way, so that you know conceptually what are these kinds of wave we have here. So for the plane waves, let's consider XYZ coordinate system, Cartesian coordinate system. Assume that in the xy plane there is an infinite current set which is directed along the y-axis. Such kind of infinite current set will be giving me a wave which is producing wavefront which is in a plane, different planes. So wavefront for this kind of current set will be like a plane, So such kind of source current set will be giving me plane waves. And look at the direction of the wave vector. Wave vector will be along the z direction. So now you observe that wavefronts are planar and direction of the wave vector is perpendicular to the plane. So these are the two conditions satisfied. So such kind of source current set will be giving me plane waves. There is another way of looking at the plane waves. See, basically, let's say you even consider a isotropic radiator point source. It was radiating fields everywhere in space and it gives you spherical wavefront. These are the spherical wavefronts. Let's say you consider a point where the r is tending to infinity. So you assume that you are observing this wave at a distance r which is tending to infinity. At that distance, this spherical wavefront will turn out to be almost like plane. So in that case, what we are observing is that when we are observing even the spherical wave in the infinite distance from the source, the spherical wavefront is almost like plane waves. So any kind of source in the far field at a very large distance, we can actually assume plane waves. And you can observe that direction of wave propagation is along the wave propagation vector is along the z-axis. So this is the case where you have a source at infinity. First case was when you have a planar sheet. Planar sheet gives me plane waves, and spherical source or point source, when we observe it at infinite distance, it also behaves like a plane waves. There is another way of looking at the plane waves. For example, you have an antenna which is very far away from a point source. It's not at infinite distance, but it's very far away, far enough that the wavefront which this antenna aperture is capturing is almost like straight line. So if your observation point is far enough such that the wavefront, the antenna which is capturing that wavefront, spherical wavefront, may actually look like straight line for that antenna. So in a very far away distance where your wavefront is almost like a straight line for the device which is capturing that wavefront, then we can even consider this as a plane wave. So that's a practical way of defining plane waves in a very far away distance from an antenna. Okay, so we have discussed about the plane waves. We want to find the equation for this plane waves. First thing is we observe is that for the plane waves you can have a 2D source, two-dimensional. So we have a planar sheet which is two-dimensional. In our case, we consider it was in the xy plane. It can be in any plane. Or we can have a source at infinity. So such kind of sources will give me a wavefront in the form of planar surface. And you know that this planar surface was infinite plane, so the area was fixed. So the amplitude of the wave will also be constant because the area was constant. So now for the planar waves, amplitude is constant. It doesn't change with the distance. First observation is that. So simply we can write the expression for such kind of planar wave function as simply as b0 cosine of omega t minus beta z. Amplitude is not changing with distance. And you see that the phase of the wave omega t minus beta z is dependent on both space and time. So we have a planar wave. Now this is the equation for a planar wave. Simple expression b0 cosine of omega t minus beta z. Amplitude doesn't change. So we also call this as uniform plane waves. Amplitude doesn't change. And phase is changing with respect to time and space. So now let's say the wave we have assumed. So the wave we have assumed was moving along the z-axis. So now wave can move in any arbitrary direction. I cannot say to the wave, hey, you go in along this particular direction. it can move in any direction in the xyz plane. So now in that case, your wave vector will be having three components. Wave vector will have three components, one along x-axis, one along x-axis, y-axis, and z-axis. So beta is a vector now. It will have beta x, beta y, and beta z component. And your position vector now will also be having three components, x, y, and z. In that case, what is the equation of the wave? We can extend the expression for the equation of the plane wave, which is moving in the xyz plane, in the xyz region. So now this equation of the wave will dependent on the time x, y, and z. So for that particular case, equation of wave can be expressed as b0 cosine of omega t minus beta x x. Beta x is the component of the wave vector along the x direction. Beta y y minus beta z z. Beta y is the component of the wave vector along the y direction, and beta z is the component of the wave vector along the z direction. So now this is a more generalized expression of a plane wave moving in the any arbitrary direction in the xyz region. So now this can be again expressed in the exponential form. We can write this in exponential form. We have seen that the exponential form, when we take the real part of it, we get the equation of the wave. So what is the exponential form for this? b0 real part of exponential j omega t minus beta x x minus beta y y minus beta z z. So now we can write this even in a vectorial form. So expression for the wave will be b0 real part of exponential j omega t minus beta vector dot r vector. So this is the equation of the plane wave, and we will actually mathematically derive the equation for cylindrical, spherical, and plane waves from the wave equation. Wave equation, we can easily get it from the two Maxwell-Curl equation. We get the wave equation, then we can derive the expression for cylindrical, spherical, and plane waves in exact form. Now, whatever discussion we have done in this class will be intuitive way of getting an expression for the cylindrical, spherical, and plane waves. And what we'll be doing in the next class will be the exact form. Using the Maxwell equations, we derive the wave equation and find the proper expression for the wave equation, cylindrical, spherical, and plane waves. Thank you.